Today we're going to cover Cramer's rule from chapter 9. And the way this works is if we're trying to solve ax equals b and we have an invertible matrix A, then we can find the solution using this formula right here. And now the real question is what is this a sub I here? And so I figure I'll answer that while we're doing an example, and once we get used to the procedure, maybe we'll go in and we'll create a function that will perform Cramer's rule. Okay, so the first thing we need is a matrix A. And so how about we go 3, 1, 0, and minus 1, 2, 1, and minus 1, minus 1, 2. Okay. There it is. We can go ahead and suppress that. And actually, let's make this corner right here, let's make that a 0. Alright, and we're also going to need a b. So b will be 5 minus 2 minus 1. There it is. So we have a column vector. And our goal will be to find some vector x. Okay, so you don't want to code this part, but so x1, x2, x3, and we'll be again using this formula up here to find x1, x2, x3. Alright, well, let's go ahead and we will start off with creating a sub 1. Okay. So a sub 1 here. So what we're going to do is we're going to take b, okay, and we're going to replace the first column of A with B. Okay. So A will look pretty much the same, so maybe I should just copy and paste it. And we'll just change that one column. Okay, so this should become a 5, a minus 2, and a minus 1. And while we're at it, why don't we just compute the rest of these? A2. So A2 will just replace the second column with B. And I'm going to do the same thing here. And that vector B is, again, 5 minus 2 and minus 1. Looks good. And let's do A3. There we go. And then finally we'll replace the last column with B. So 5 minus 2 and minus 1. Okay, there we go. And if we wanted to find x of 1, let's say, okay, that's going to be found by taking the determinant of a1 and dividing that by the determinant of a. And we're going to do basically the same thing for x2 and x3. Other than we'll just change these to 2's and 3's. Okay. And is what we'll do as soon as we're done with this is we'll compare our answer that we get from using Cramer's rule and compare it with if we were using the backslash command. Okay. So let's first make sure everything's suppressed here. Other than maybe in the end I'll make it display x. Okay. Yeah, looks good. Let's go ahead and run it. Okay. So we have some answers. The question is, are they the right ones? Let's see here. Let's maybe call let's call this other one maybe xb for using a built-in function. Okay. And so again, is what we'd like to do is a backslash b. Let's move this up and see if we have the same thing. Yep, same answer. So it looks good. So is what we're going to do now is we're going to switch over to another tab and we're going to create a function that will perform Cramer's rule for us. Alright, so I have switched this over to a new tab here, and our Cramer's rule function I'm going to name CR. Again, the name of the function and the file name should match. Okay. And I think if you have the time, it would be a good idea to actually try and code this function yourself, because I think it has some interesting issues that pops up as you try to code it. Okay. Alright, but let's go ahead and we'll get into this. Okay. So the first thing I want to point out is every time we do this, we'll be computing a determinant. Okay, and in fact we'll be computing two determinants. Okay, for every iteration of a for loop that we're going to make here in a moment. Okay, so outside of the for loop that we'll have, I'm just going to write for the moment. Okay, outside of it, it would be a good idea to just compute the determinant of a. And let's just maybe name this determinant of a. Okay. All right. And it again is what I'm saying here is we're going to calculate this once rather than over and over again in the for loop. Okay. So that's automatically assigned there. Okay. Now the next question is how many calculations are we going to make, right? We want to be using, let me find the right tab here. There it is. We want to be using these three formulas here if it's a 3 by 3. And if it was a 4 by 4, then we'd have 4 values of x that we'd want. And if it was a 5 by 5, we'd have 5 values that we want. But it's this formula here we want to use. And again, it's really based on the number of calculations that we have to do here is based on really the size of the matrix. So maybe we'll start off with actually thinking about the size of A. And why don't we call the outputs M and N? Okay. All right. So it doesn't really matter which one we pick here. We could say for I equals 1 to M or 1 to N because A needs to be a square matrix. Okay. I'm going to just say 1 to N. But that being said, since it does need to be square, maybe before anything happens here, maybe we can put in an error message. So maybe if M is not equal to N, let's say error not a square matrix, because that would be problematic. All right, and then what next here? Okay. Another actual error message we could build in. We mentioned we were going to compute this before we do our for loop, right? Well, maybe it'd be a good idea to see whether this determinant is 0 or not. Because if it's 0, then it's going to be not invertible, and this formula is not going to work. Okay, so maybe we should build in another error check here. But let's end this first one. There we go. So this time, if the determinant of A, okay, if the determinant of A is equal to 0, is what we'd like to say is error. A is not invertible. All right, now maybe we can start our for loop here. Okay, so no matter what, if we go back and look here, the row of A that gets replaced is equivalent to whatever the subscript is here. So we first replaced column 1, and then column 2, and then column 3. So for this little formula here, A, the only difference between each A is just where B is in A. Okay, so let's go ahead and switch back here, and let's maybe at least get that part in there. Let's say maybe, what do we want to call our matrix here? We could just call it, let's just call it mat. Okay. So we'll say MAT for matrix. Okay. And we just want to assign the ith column a new value. Okay. So is what we'd say here is if we want the ith column is colon comma I. Okay. So that does every row in column I, which is another way of just saying column I. And we'd like this to come from B. Okay. And then next, the question is this submatrix that we're creating, the rest of the columns should match the columns of A. So okay, the question is, you know, what are we going to do here? Okay. Well, again, we're going to be replacing columns. Okay. But we don't want to replace all of them. Okay. I'm going to put in a little bit more code here. So is what I'm going to try and put here is, let's take certain columns of A and put them in mat. Okay. The only one we don't want to do here is column I. Okay. So we could actually add in maybe a little if statement here. Okay. And maybe one more for loop. So let's go ahead and we'll put the for loop in here first. And this one's going to be so that we can run through the rest of the columns of A. Okay, because so far we've only done the ith. Okay. So we'll go 1, 2, n still. Okay, but we only want to be performing this operation that we'll put down here, which we haven't yet. This calculation, we only want to perform it if j is not equal to I, because we've already taken care of that ith column. Okay. And we want this to be in column J. Okay. So we're taking the jth column of A and assigning it to the jth column of mat. Okay. And the ith column of mat is B. And again, all we're actually trying to do here is calculate that matrix A sub 1 or A sub 2 or A sub 3 that we were talking about in our previous script. Okay. So we need to end our if statement, end a for loop, and then end the other for loop. But we may not be done here yet. Okay, so once we've completed the matrix mat, is what we'd like to do is compute x sub I. Okay, right? X sub I. So this is outside of the inner for loop. So this is only going to compute for each I here. We don't have to worry about it getting mixed up with this. Okay. So we'll have an x sub 1, an x sub 2, all the way up to x sub n. Okay. And the way we compute that again is the determinant of, and we'll just say mat here, because for every time this for loop runs, mat is going to be a new matrix. So we can just say mat, and then we could divide this by the determinant of A, which we've already calculated, so we don't need to repeatedly calculate it. So that's why I'm just using this rather than the actual DET of A. Okay. All right, and let's see if we have any unsuppressed stuff. We probably don't want to see this calculated every time, or this, or even this. And is what I'd like us to do is let's go test this out, see if we get any error messages. And if we don't, maybe we'll add in maybe a few more error messages. Okay. Let's save this. And actually, I'm going to add one last thing here. I want that output X. Okay. So I'm going to name this X sub CR, and we'll put in our matrix A. And I just realized that we are missing one other thing. We need a vector B. Okay, so let's go back in here. Oh, and we already had it. We have A and B as an input. Good, good. Okay. All right, let's go ahead and run. Let's see where our error's at. It says at least one end is missing, and I believe it's on one of our if statements, maybe at the top. Let's go see. Yep, it's right here. Okay. So let's go ahead and save, and we'll rerun that. So we have X and XCR, both are the same. So that looks good, and you can see that that matches also with the built-in function with the backslash. Okay. So it looks good. Let's maybe add in, though, a couple more error messages. Okay. So another thing that would be problematic would be if the number of rows of B didn't match the number of columns of A. Okay. So we could check that. We would need to know the length of B, though. Okay. Let's say K and L for the dimensions of B. Okay. So the first thing here is if the number of columns of A, so that would be n, okay, if that number is not equal to, so I'm going to put not equal to, the number of rows of B, which would be K, then this equation here isn't going to make sense. And the product A times X won't give us the right dimensions for B. Okay. So is what we'll say here is if this happens, actually let's just make it simple. Number of columns of A does not match number of rows of B. and we just need a little end on that. Okay. And we could even add in another one. We could say, hey, if B is not a column vector, we have a problem. Okay. So if, okay, so for it to be for one, a column vector, okay, or just saying that it's not a vector, we would be able to spot that, okay, if it had multiple columns. So if L was greater than 1, we have a problem, okay? Because that either is implying that we have a matrix or it's implying that we have a row vector, which would be bad. Okay, and I think that is enough built-in error messages. Okay. And that is it for today. We'll get into Gaussian elimination tomorrow.